here is the relation between different types. There is no relation between almost sure convergence and Heung-No convergence. There is some relation between almost sure sense convergence and improbability. That is, if xn converges to x, almost sure sense, it implies that xn converges to x in probability. But converse is not true. That is, xn converges to x in probability does not imply xn converges to x almost sure sense. So almost sure sense is a stronger condition than convergence in probability. Okay, the same way Heung-No convergence and convergence in probability. So Heung-No convergence is stronger than convergence in probability. We will talk about certain examples of almost sure sense and probability sense in the following note. Okay, so here we want to show almost sure sense convergence implies convergence in probability. Xn converges to x, almost sure sense, implies that for each epsilon, limit k goes to infinity, probability of set of omega, unions of these events is equal to 0. So this one is by the definition of almost sure convergence. And we compare this set with the set of omega for convergence in probability. So let's consider this set for particular k. So xk deviates from x by epsilon much. So that is the set of omega. And on this side, we have same set of omega parameterized by n. And I have unions of such a set for n greater than or equal to k. So this right-hand side is equal to probably better to write a couple of items. So the right-hand side is a union. So that union says set of omega x and omega minus x omega greater than epsilon union with omega x. So let's start with the k, and the k plus 1 omega minus x omega greater than epsilon union omega xk plus 2 minus x omega greater than epsilon. So I can continue this to the infinity. So which one is larger, left-hand side or right-hand side? As you can see, this set appears right here in the beginning. And that this one is union with another set, union with another set, and so on. So this set must be smaller than or equal to the right-hand side set. So if I take the probability of smaller set, I mean, that probability should be less than or equal to probability of the union set. Okay, so that's the fundamental result from probability theory. Then the probability axiom that we studied in the probability primer. Then we, after you have done that, we take limits on both sides with respect to k. Then limit k goes to infinity, we take both. This is nothing but almost a sure sense convergence. And we say that this one is equal to 0. So the bigger goes to 0, the smaller has to go to 0 as well. End of proof. So when xn converges to x, almost a sure sense, xn converges to x in probability as well. Okay, so we have proven almost a sure sense implies convergence in probability in previous page. Here we want to show converse is not true in general. When something is not true, when a statement, when we want to show that a statement is not true, we can just need to provide a counterexample. Okay, so the counterexample that we want to show is that xn converges in probability, but xn does not converge to x almost a sure sense. That's what we want to show. So here is a counterexample. So consider a series of random variables xn. Hold on. This xn is defined to be indicator function of an. So this indicator function is 1 if omega belongs to an, 0 otherwise. Okay. So a1 is given to be this. So a1 is in this interval. So x1 is 1 over that interval. Now, let's take a look at x2. x2 has a2 as an interval. So x2 is 1 over 0 to half interval. So in this interval, it is 1. And outside this interval, it is 0. Now a3 is in this interval right now. And then let me clear it. So x3 is 0 over here and 1, oh sorry, 1 right here. Okay. All right. So x1 0, 1 0, x2 goes something like that, 0 outside, and so on. And then x4 goes like that and 0. x5 goes like that and 0. x6 goes like that and 0, and goes like that and 0. As we increase n, what do you think will happen? Obviously, either the xn will travel with a smaller support, goes from 0 to 1 interval like this, with a smaller and smaller width. Smaller and smaller, the width getting smaller and smaller. It sweeps across the interval from 0 to 1. Okay, it will continue to come back to 0 and sweep across toward 1, and then once it reaches 1 with a smaller window size, it sweeps across again, and again. So that's what the random variable xn is. The value of 1 with a certain support sweeps across the interval from 0 to 1. Now, let us now further define the probability. The probability of xn equals to 1 is defined to be length of that interval. So probability xn equal to 1 is the length of the interval. That means in the case of x1, the probability x1 equal to 1 is 1, okay, over this interval. So that's the probability. So the probability x1 is equal to 1 is equal to 1, okay, over omega from 0 to 1. And we let x to be equal to constant 0. So x is 0 all the time. X is 0. Okay. Now let's take a look at probability that x2 is equal to 1. So what is the probability that x is equal to 1? So the length of that interval is half, so it is half. About the probability x3 is equal to 1. So length of that interval is half, so this is half. What about the probability of x4 equal to 1? That is quarter. How about probability of x7 equal to 1? That is a quarter too. All right. We have covered that one. We have covered this one. Now we want to figure out the probability of this set right here for each omega. So probability that xn deviates from 0, x is equal to 0. So deviates from 0, which is, that is the case when xn is equal to 1, right? That x1 is equal to 1, as you can see, because it's a Rebec measure. As the length of the interval getting smaller and smaller, as n goes to infinity, that probability goes to 0 as n goes to infinity. So this random variable converges in probability. Now let's see if that means convergence in almost sure sense. For almost sure sense convergence to hold, we need to consider the set of omega where xn converges to x. So we, in order to see this, let's consider any omega. So any omega, and let's take a look at xn is equal to 0. So xn is equal to 0. So for any omega. So consider this omega, let's say omega 0.1. So x1 omega is 1. Okay, that is different from 0, but let's consider xn omega. So x4 is equal to 1. X4 omega equal to 0.1 is equal to 1. What about, is there a larger xn is equal to omega, is equal to 1 at omega equal to 0.1? Do we have such xn omega equal to 0.1, which is equal to 1? Yes, of course, because this one, once it reaches the 0.1 with a smaller window size, like in this case 1/8, it sweeps across the whole interval from 0 to 1. And then with an even smaller window, it do that again and again and again. So there exist many xn's omega equal to 0.1 that is equal to 1, which is a deviation from x equal to 0 at that omega. So omega 0.1 does not belong to this set right here. How about you choose any other omega and do the same? For example, let's say 0.5. 0.5 does not belong to this set either. So if I continue this experiment for each and every omega in this interval, I notice that xn is not equal to x. So the whole interval from 0 to 1, the collection of all omega, xn is not equal to x. So this set right here, when xn is equal to x, is a null set. So the probability of a null set is equal to 0. So that means xn does not converge to x, almost a sure sense. So it is not true. Okay. So in this particular example, we have convergence in probability, but almost a sure sense convergence is not obtained. So here is a counter example of convergence in probability does not mean convergence in almost sure sense. So with this counter example, converse is not true has been proved. Now in this example, convergence in probability and convergence in almost sure sense. So in this example, both are satisfied. So here we want to consider a series of random variable xn, which is indicator function of an, but here an is defined differently. So a1 is the interval from 0 to 1. An is interval from 0 to 1 over n. So as we can see, this interval is a1 right here, 0 to 1. So it's 0 to 1.0 right here. And then a2 is right here from 0 to half and 1/3 and so on. So the random variable x 1 is this, okay? So x1, and we compare that with x equal to 0, and x1 is this, x2 is this one, and 0 here, 1/3, it is 1, and 0 to 1/3, it is 1, 0 in the other place. So as you can see, as n goes to infinity, the xn is 1 over tiny interval. Rest of the interval, it is 0. And then as you can see, in this particular example, as I consider any particular omega, the random variable converges to 0. And once it converges, the case where xn deviates from x, this one does not appear again as I increase n. So for each omega, this thing stops appear as I increase n significantly large. So for each omega, xn omega, x omega greater than epsilon, and probability of such event goes to 0. Okay, and not only for one omega, but when I consider whole set of omega where xn limit xn is different from x, when I consider all the omegas that limit xn is equal to x, it becomes the all omega within the interval 0 to 1.0. So whole set in this particular becomes this set. Okay, so probability of such a set, probability of this set is equal to 1.0. So that's the convergence in probability. Also convergence in almost sure sense example. So that's the example for both.